Hi, I'm here today to talk to you guys about the atmosphere. So we're starting to cover the content in chapter 9. We're skipping chapter 8, which is about environmental toxicology. And unfortunately, we just don't really have time to go through that whole thing, although we will address parts of that chapter when we talk about water quality and air quality and waste. So we will address some of those topics, but just FYI, as you're reading along, we're moving on to chapter 9. So I'm going to share my screen so that we can kind of look at the PowerPoint slides. All right, so from the beginning. So first of all, everybody, I think, is familiar with the atmosphere. We've all been in the atmosphere before. We know where it is. We can point up to it. We can breathe it in. And maybe we couldn't define it very well. So our atmosphere is basically the space around our Earth that is covered or populated by gas molecules. And those gas molecules are held close to our Earth because of the Earth's gravitational field. The mass of the planet is attracting the little molecules that have their own mass. And I like this particular picture of the Earth because basically you can see how thin the atmosphere is relative to the Earth. When we're standing on the ground and we look up in the sky and see all the clouds and see all the weather, it seems like stuff is very high up, but it's actually quite close to us relative to space. And so basically, as you look at this picture, you can see that the areas that are really bright are bright because there's lots of molecules reflecting lots of light. And then as you go higher up above the Earth's surface, there are fewer atmospheric molecules. They're more spread out up there. So they reflect sunlight, not as much light. And then eventually the space just turns dark. And that's because there's basically no more molecules out there. And that's when we enter space. So our atmosphere is this kind of relatively thin layer around the Earth's surface that contains these different kinds of gases, things like oxygen that we breathe in and other gases in the atmosphere. So you might already know, we talked about this when we mentioned the nitrogen cycling earlier in the class, that nitrogen is by far and away the biggest component of the Earth's atmosphere. We don't think about it a lot. We don't talk about it a lot because it's a pretty inert gas. It's not very reactive. But it forms 78% of the molecules in the atmosphere. And then we have oxygen at about 21%, argon, another thing we don't hear about a lot because it doesn't react with much, doesn't have a lot of activity. And then all the other things, carbon dioxide, other greenhouse gases and pollutants that we talk about may have big impacts on life, but they actually form very small percentages. Carbon dioxide is only 0.036% of the kind of content of our atmosphere. So the atmosphere is not all the same. It behaves a little bit differently at different levels above the Earth's surface. And so there's 4 different levels, and I'm going to kind of talk about them as we are approaching Earth. So starting high, way up above the Earth's surface, if you are like a meteorite or something that's entering the Earth's atmosphere, the first thing you would encounter is a layer that's called the thermosphere. And the thermosphere is this area of rapidly increasing temperature. So the average temperature of molecules up in the thermosphere can be pretty hot. And basically, the most likely interaction you've had or visual acknowledgement that you've had with this part of the atmosphere is that this is a part of the atmosphere where we see what are sometimes called northern lights or aurora borealis. They also have southern lights in the southern hemisphere. So we don't see this around in Quincy, but you've maybe seen pictures of this or visited places where you've seen this up close to the North Pole. And in this case, what's happening is we have these charged particles coming into the Earth's atmosphere as part of what's called the solar wind. The sun is setting off energy, but also some little things like electrons and whatnot in this plasma. They're entering the Earth's atmosphere. They're energizing some of the molecules that are in the upper atmosphere, and then those molecules are released, or those atoms and molecules are releasing light, and that light forms these neat light shows that are called the northern lights. if they're in the northern hemisphere. So this is kind of the first layer of protection that the atmosphere provides to us as inhabitants of the solid Earth's surface. It is basically interacting with these charged particles and kind of diffusing those charged particles so that they're not coming in contact with us on the ground. Then the next layer that you would encounter is called the Mesosphere. And the Mesosphere has some of the coldest temperatures in the atmosphere. This red line that's zigzagging through this diagram of the atmosphere on the right is showing temperature changes. So the upper Mesosphere has the lowest temperatures in the whole atmosphere. And the way that you have probably observed this part of the atmosphere before is that this is the place in the atmosphere where shooting stars can be observed. So higher above the Mesosphere and the Thermosphere, the atmospheric molecules are so spread apart that there's not enough basically friction that can be created between the molecules to get enough energy to cause things to ignite or start to combust. But in the Mesosphere, the atmosphere starts to get a little bit denser. And so as a solid chunk of rock enters the Earth's atmosphere, it starts to collide with all these molecules. And the pressure, the high pressure of all these things kind of rubbing against each other creates enough heat energy for this rock to ignite, and then we can see it as a shooting star. So you've looked up in the night sky and certainly seen the Mesosphere before. And that's also good. Burning up these pieces of solid that are entering our Earth's atmosphere means that fewer solid pieces are pummeling us on the ground. So this is kind of another layer of protection that our atmosphere provides to surface inhabitants. Okay, then we enter the stratosphere, and the stratosphere is the first layer of the atmosphere that you may have actually entered before. If you've been on like a cross-country flight or an international flight, you likely kind of flew up above the clouds and got into this layer of the atmosphere that's called the stratosphere. This is a zone where the temperature as you go up through the stratosphere is increasing, which is really different than the troposphere below that we'll talk a little bit more about next. And probably the most important component from an environmental standpoint of the stratosphere is that it is home to the ozone layer. So we'll talk more about ozone layer when we talk about atmospheric pollution next week. But ozone gas is this gas that has 3 different oxygen atoms all bonded together. And it is a gas that is very good at absorbing and reacting with ultraviolet radiation, which is one of the types of energy that travels here from the sun. And ultraviolet radiation is not good for us, right? That's why we put on sunscreen. It can give us sunburns, it can give us skin cancer, it can damage other living organisms as well. And so we want this layer of ozone gas in our stratosphere to help kind of diffuse this ultraviolet radiation. And as you may be aware, we've had some pollutants, atmospheric pollutants that have kind of started to break down some of the ozone. So we've outlawed many of those pollutants, and hopefully this is a problem that's on the mend. But anyway, that is where the ozone exists, up in the stratospheric layer. So the stratospheric layer is kind of above about 8 miles up to about 30 miles, or you could think in terms of metric, about 10 to 50 kilometers above sea level. Okay, so that's a different layer of the atmosphere, also providing protection to us. And then the final layer of the atmosphere is called the troposphere. And the troposphere is the layer that encases the actual Earth's surface. So all of the Earth's surface, even the highest peaks, places like Mount Everest, are contained within the troposphere. And also all the principal weather activity of the Earth is contained within the troposphere. So when you're looking up in the sky and seeing clouds, you're likely looking within the troposphere. And a lot of times you can see the place where the troposphere ends and the stratosphere starts, because clouds will vertically rise upwards, and then they'll run into this boundary between the troposphere and the stratosphere, and there's not a lot of good mixing between the air molecules in these layers, and so the clouds will start to flatten out. And so if you've seen either like a big plume from a forest fire or like a thunderhead cloud, or if you've seen pictures of like atomic bomb clouds, they often have these really flat tops, and that's basically the cloud or plume hitting the top of the troposphere. So that's an important characteristic. And then this is by far the densest part of the atmosphere. So there's way more molecules packed much, much more tightly together within the troposphere than anywhere else. And then also within the troposphere, the closer you are down to sea level, the denser the atmosphere is. So if you take a lungful of air in at sea level, you're getting a lot more molecules and a lot more oxygen in than if you hike up to the top of Mount Everest and breathe in the same volume of air. There's not as many molecules there, so you don't get as much oxygen, for instance. So this is why like some athletes train at high elevations. They try to train their body with low oxygen so that they can be super performers in lower oxygen environments, or this is why people bring oxygen tanks when they climb tall mountains. So that is a characteristic of the troposphere. And then the final characteristic of the troposphere is as this pattern of density changes, where as we climb within the troposphere to higher and higher elevations and have fewer and fewer molecules surrounding us in the air, that also means that the temperature of the air drops. So if you climb a mountain and you get to a high peak, it's likely to be very cold and snowy up there relative to temperatures down at the beach. And that's this characteristic pattern within the troposphere. So as we go up from sea level, the molecules are more spread out. There's not as many of them, and that causes the air to be colder at altitude relative to the ground. And that is something that affects our weather a lot. So anyway, the atmosphere is not all the same. It contains these different layers. It has important ways that it kind of protects us as inhabitants of the surface of the earth. And then, of course, provides a lot of resources like oxygen that we need to be able to live, and water that we need to be able to live. Okay, so another important consideration is that the atmosphere is this kind of filter that through which a lot of our energy that we use on the Earth's surface kind of moves through. So where do we get our energy from? I think many of you guys know that it doesn't originally come from your electrical socket or from your pump at the gas station, but originally almost all those forms of energy were derived from the sun. So geothermal is a different issue, which we'll talk more about later, but most of our energy at some point, either today or a week ago or 400 million years ago, kind of was captured because of energy that was arriving here from the sun. And you will hopefully remember from our discussion of energy basics earlier in the semester that energy comes in different forms, and it moves as waves. And in particular, there's a kind of a dominant form of energy that is electromagnetic radiation. So that's many kinds of energy, not including things like sound. But many of the kinds of energy that we interact with are types of electromagnetic radiation. And the sun sends out electromagnetic radiation towards us in a spectrum, in a range of different types of energy that have different sized waves. So the spectrum refers to these different range of wave dimensions that have different properties. And so we know visible light energy, the energy that we can actually see because we are evolved to be able to be kind of tuned in with this type of energy, are in the 400 to 700 nanometer wavelengths. Waves that are slightly smaller than that are ultraviolet radiation. Even smaller than that are X-rays and gamma rays. Waves that are slightly bigger than that are heat, infrared radiation, then microwaves and radio waves. And our Earth receives primarily visible light energy. That is the type of energy that we receive the most of from the sun, closely followed by infrared radiation or heat radiation. So as we mentioned before, as humans, we're very tuned, or as organisms that live on the Earth's surface, we're very tuned into light and heat because those are the energy sources that are abundantly around us. But we also get ultraviolet radiation. Much of that is filtered out by the ozone layer and the stratosphere. And then we get very small amounts of other kinds of radiation that are traveling towards us as well. So our energy is coming through our atmosphere from the sun and landing on the Earth's surface. And so when we're thinking about how this energy is arriving, we will start to think about how that might affect the climate or the temperature in particular, which is only part of climate, but the temperature of the Earth's surface. So when we are trying to think about how hot or cold it might be in any given place at any given time, we need to kind of think about how much energy we're receiving from the sun as filtered by our atmosphere. And then we also need to consider how much energy we might be losing back out to space, because not all the energy that comes in stays here, right? So I kind of think about this as a checking account analogy, right? You get paid, you get some money, it comes into your checking account, but then if you want to think about how much money you already really have in your checking account, you can't just look at your paycheck. You also need to think about, like, how much did I spend on gas, or how much did I spend on groceries or rent, or all these other kind of expenses, ways that the energy has been funneled out of your bank account. So energy from the sun arrives and then also leaves our Earth's atmosphere, and we need to understand both processes to understand how much energy is actually here, so that we can understand the climate of Earth at any given time. So we have kind of an equation that I laid out for you. So when we think about how much energy arrives at our planet, we call that incoming solar radiation or insolation. And we know that that amount is actually not fixed, but it varies over time. It varies both over time to the whole Earth, and then it also varies because certain parts of the Earth might be getting more or less energy in a given season or a given period of time. So there's some variations there. So we're going to talk about that a little bit. And then we're also going to think about what are some of the ways that energy might be lost from our atmospheric system. And so in those cases, we're going to think about the reflection of energy, the reflectivity of the Earth in the clouds and the atmosphere. And then we're also going to think about greenhouse gases, because they have an influence on energy storage versus energy loss in our atmosphere. So this is kind of like a template of the discussion that we're going to have next. And again, to summarize, it's all about thinking about how the climate of our planet might be at any given time in Earth's history. Okay, so first of all, I just want to say that the energy that we receive as Earthlings from the sun depends on how close we are to the sun, right? If you're trying to get warmed up by a heater, if you stand closer to the heater, you're going to get warmed up faster. But it also depends on the angle, the way that the Earth is turned or tilted or curved relative to the sun. Okay, so same thing. If you're trying to get warmed up by a heater and you stand directly facing the heater, you're going to get a little bit of a different energy input than if you're turned and your shoulders just touching the heater or some other part of your body. So the angle, as well as the proximity, the distance, has an impact. And so there's a variety of different ways that the Earth-Sun geometry, the kind of the distance and angle of these two bodies, changes over Earth's history. And the first one of these that we talk about is called obliquity, and this has to do with the angle of the Earth's axis. So as you probably know, the Earth is not oriented in such a way that the North Pole is actually pointing straight up and the South Pole is pointing straight down. If you've ever seen a globe, you know that the North Pole is actually tilted a little bit. And that tilt is actually not always the same, but the Earth is actually wobbling a little bit. And as it wobbles, certain parts of the Earth are tilting closer to the sun and tilting away from the sun. And not only is it's not really so much of a distance thing that they're getting closer in a way, but they're changing their angle. So they might be getting blasted really directly with light, or they might be turned in such a way that the sunlight is not hitting them so directly, which would make them cooler. So this obliquity is something that's very directly tied to the seasons that we have on the planet. When we're more tilted, we have more extreme seasons. When we're less tilted, we have less extreme seasons. And this whole tilt, or this obliquity pattern, is something that we know cycles on Earth and changes over about a 41,000 year cycle. So this is something that's constantly changing over Earth's history that impacts our energy input and therefore our temperature and climate. The second component that is kind of a geometry issue is something that's called eccentricity. So you may have learned back in elementary school that the sun is at the center of the solar system, and then the planets move around it in a circle, and that's roughly accurate, but that is actually not really a circular path that planets travel on. Instead, they travel on elliptical, kind of like oval-shaped patterns. And what we have observed is that the Earth actually does not always travel on the exact same elliptical pattern, but sometimes that ellipse is more squished and elongated, and sometimes it's much closer to a true circle. So this eccentricity refers to kind of the squishing and then unsquishing of this elliptical pattern around the Earth. Sometimes it's very eccentric, very squished, sometimes it's less eccentric. And when this happens, or when these changes occur, it causes the Earth to sometimes be closer to the sun and sometimes be farther away from the sun, and sometimes have certain seasons when it's closer to the sun, and certain seasons when it's farther away from the sun. And this is another thing that affects how much energy arrives at the planet, and therefore how hot the planet would be and what the climate would be like. I guess another thing I should mention is that the sun is also not quite at the center of the elliptical pattern. And so the more squished or eccentric the elliptical pattern is, the more offset the sun is from the center of the Earth's orbital path. So that is kind of another component as well. Anyway, this affects seasons, affects energy input, and it takes about 400,000 years for the pattern of the Earth to kind of go through a full cycle. So this is kind of another long-term geologic scale change that impacts Earth's climate. And then finally, there's a concept that's called precession, and precession is kind of another geometric shift that happens that has to do with the way that the Earth's axis is tilted. And in this case, it's not so much about how extremely tilted it is, what's the angle of the tilt, but it's more about which direction that tilt is pointing. So you can kind of think about the Earth wobbling not only back and forth, but also kind of in a more like forward, backward, or in reality, more of a kind of a circular direction. And so this is another thing that is going to affect not so much the distance between the sun and the Earth, but kind of the angle between different parts of the Earth and the sun, which again can affect seasons and therefore climate. And this is something that changes on a slightly shorter time scale, about a 26,000 year time scale. But again, kind of a longer geologic scale process that affects energy input and climate in our Earth system. Okay, so all these three things together are called Milankovitch cycles. So if we combine the impacts of changes to the Earth's angle that we call obliquity, changes to the Earth's orbital pattern, which we call eccentricity, and then changes to the Earth's kind of axis direction that we call precession, we combine the impacts to the Earth of those three things, and we refer to the long-term climate impacts of these changes as Milankovitch cycles. So in the graph that I am showing you on this slide here, I have in blue a line that's kind of the smoother line that's showing the solar irradiance, or kind of the imagining the total solar input that we would have to our Earth over time as estimated based on our understanding of Milankovitch cycles. So you can see it's not always the same energy input. Sometimes it's higher, sometimes it's lower. Okay, and then in purple, this more kind of rougher type line is something that's estimating the temperature of the Earth going back in time. And you can see that the temperature of the Earth is sort of roughly correlated, right? Roughly following along with the blue line, but it's not a perfect match, okay? So it seems like by this kind of rough correlation that the Milankovitch cycles are a factor that could be contributing to changes in our Earth's climate. They're one potentially causal factor. We have a reason to believe, because we understand how energy works, that if energy changes, the Earth's climate would change in response. So we think this is one of the causes of shifts to the Earth's temperature, but not the only one, because there's certainly times when we have high solar irradiance, high energy input, but it seems like the temperature is still low. And so there's probably some other factors that are influencing climate as well. But nonetheless, these Milankovitch cycles are one of the kind of long-term climate impacts that result in changes to energy input to our planet. Another thing to acknowledge is that not all parts of the Earth receive the same input of energy from the sun. So we have basically a curved surface. Our Earth is curved, right? It's rounded. It's not just like a flat thing that's facing the sun. And so in the figure on the right, you can see that as the sun's rays are hitting the Earth, closer to the center of the Earth, closer to the equator, the vertical rays are hitting the Earth pretty directly, almost at a right angle, a 90-degree angle. And what that means is that they're actually hitting a relatively small area of the Earth's surface. And so there's a lot of concentration of energy focused on that part of the Earth's surface that heats it up pretty effectively. Whereas if we're in a curved part of the Earth that's close to the poles, it's kind of facing away from the sun, the same energy from the sun hits that part of the Earth at an angle. And so that same amount of energy is being spread out and used to try to heat a much bigger area of the Earth's surface. And what that means is that there's actually less energy hitting each piece of land area, or there's a lower concentration of energy on the land. And so it's not going to be as hot in these parts of the Earth relative to places closer to the equator that are getting this very concentrated energy. So even at the same period in a Milankovitch cycle, the equator is going to be having a different temperature and a different climate relative to somewhere at a higher latitude, which is to say an area farther away from the equator, closer to the poles. Okay, and this is one of the reasons that we have seasons. So the Earth's axis, as we just said before, is not straight up and down, it's tilted. And as that tilted Earth moves around the sun, the tilt is always in relatively the same direction. Okay, so in certain times of the year, the northern hemisphere where we live is pointed kind of away from the sun. So it's at an angle such that it's not getting a very good direct hit of light. And also as it turns around throughout the day, it is spending less time just actually facing the sun. So we have more hours of dark rather than daylight hours in the winter in the northern hemisphere. And then at that same time that we're experiencing winter, the southern hemisphere is tilted in such a way that it's pointing towards the sun. So it's just getting this kind of direct, concentrated hit of energy. And also, as it turns around, it is having more hours facing the sun, so more daylight hours versus nighttime hours. So we are experiencing opposite seasons from the other hemisphere. And then 6 months later, we see the opposite thing, where the northern hemisphere at the end of June is pointing in such a way that it's facing the sun, and the southern hemisphere is facing away from the sun. So we experience our summer in June when Australia or South Africa experiences their winter. Okay, so just want to kind of acknowledge that when we think about kind of the energy budget on our planet, it's not the same for everywhere on the planet. It, of course, changes based on your position and based on the season. And I think this is something that we kind of intuitively know, but it's important to keep in mind when we're trying to understand how the climate functions in different places. Okay, so all that we've talked about so far is thinking about our energy input, how much energy is arriving at the Earth system from the sun. Okay, so we said that's one of the things that we need to understand. We want to understand the Earth's temperature and climate. But then we also said we should consider an additional factor, which is how much energy might be lost from the Earth system. Right? Just like our checking account, and we want to know how much money we have in our checking account. We can't just look at how much money was in our paycheck. We also need to look at our expenses. So when we think about our Earth's energy budget, we can't just think about how much energy we're getting from the sun. We also need to have some acknowledgement of how much energy might be lost. Okay, so there's two factors that we mentioned at the beginning of this discussion: the reflectivity of the Earth and the Earth's atmosphere, and greenhouse gases. So we'll talk about reflectivity first. Okay, so reflectivity is sometimes called albedo by scientists. So we have a reflective surface. We say it has a high albedo, an albedo of 1, and we have a very absorbent surface on the other hand. It has a very low albedo. It doesn't reflect very much. It absorbs energy instead. And this is something that changes over the Earth's history. We have not always had the same albedo because different surface materials absorb energy well and other surface materials reflect energy well. So currently, the average is that about 70% of the SR or solar radiation that arrives here is absorbed. But then the other part, 30%, is bounced back to space in pretty quick order. Okay, so I'm going to give you a minute and I'm going to ask you to brainstorm what are a few things that you are aware of that reflect radiation and what are a few things that you know of that absorb radiation. So you can pause the video if you need longer. I'll just give you a moment, jot down a few things. Okay, so maybe you've done that now. Let's think about what are the things that I thought of that reflect radiation. So maybe you thought of things like the snow. If you've ever been out skiing or snowboarding or just walking in the snow, you know that you probably want to have your sunglasses on because it's a super reflective surface. So does that mean it has a high albedo or a low albedo? High. High albedo, very reflective. Okay, so things generally that are lighter in color, so maybe that's snow, maybe that's clouds, right? These Care Bears are walking around without their proper sunglasses on. They would be miserable up in the clouds without their proper solar protection. Obviously, it's pretend, so they can survive up there, but they really should have some nice shades on. Ice and snow, and then also other things that might get into the atmosphere, like particles from a volcano or forest fires, can be reflective as well. Or other light colored surfaces, things like sand and the desert might be very reflective. Okay, on the other hand, things that are absorbing radiation well are generally going to be darker in color. Darker colored things absorb energy better. So these might be man-made materials like asphalt, roofing material. Urban areas tend to absorb energy. This leads to something called the urban heat island effect that we'll talk more about later. But then also darker colored soils or certain kinds of vegetation might absorb energy better than some of the surfaces that we talked about before. So basically, when we think about walking around on the Earth's surface, it's not always interacting with the incoming energy the same way. Sometimes it's bouncing energy back out to space, sometimes it's absorbing it, and these surface materials on the Earth have shifted a lot over the Earth's history. So sometimes we have lots of ice and snow, sometimes we have less, sometimes we have more shallow ocean, sometimes we have less, sometimes we have more soil exposure, sometimes we have more vegetation. All these things are shifting, and they're shifting the energy picture of our planet. So here's another diagram showing the absorbance of different kinds of things. So look around at this diagram, and what is something that has a really high albedo? So what's the thing you can find with the highest albedo? All right, what I see that with the highest is the snow, 80 to 95%. That's very high albedo. Something with a very low albedo, the lowest things I see are the dark asphalt, the dark roof, okay? So again, it shifts, and as we change the way that we manage the landscape, and as long-term climate changes occur to melt ice and expose soil, we are constantly shifting this picture. Here's another diagram to think a little bit about. Here's a picture of the Earth, red being highest albedo areas, and then purple being lowest albedo areas, white is like no data. So what are some areas with the highest albedo? And then think for a moment, why might that be? So some of the areas I see are like the Sahara Desert, Northern Africa, and then high latitude areas, Canada, Siberia. So in Africa, I think that would be the light colored sand, and other desert areas have that as well in the US Southwest, in the Gobi Desert in China and Mongolia, and then probably snow and ice up near the North Pole. And then lower albedo areas are going to probably be those areas that have a lot of vegetation. So tropical rainforest environments or forests along the Pacific coast or the East Coast in North America. So again, the Earth is not all the same, depending, and it behaves differently with energy depending on what's going on. Okay, so I also want to acknowledge another idea, which is called a positive feedback cycle. And this is something that we mentioned earlier on in the class. There's a question about this on our midterm. And it basically said that a positive feedback cycle is when we have a shift in the environment. And as that shift begins, it kind of creates other issues in the environment that come back and reinforce the original change. So that original change will start to accelerate in the same direction. So once you start, melting snow, then you're going to melt more snow. We'll talk about that example in a minute. Okay, but essentially, here's an example of a positive feedback circle. The Earth starts to warm up, maybe because of carbon pollution in the atmosphere. And when the atmospheric temperature is warmer, that's going to melt ice faster. And then, since the ice is melting faster, now that's shifting the albedo of the Earth. Is it making it lower or higher? Should be making it lower. We're lowering the reflectivity. We're melting ice, replacing it with soil that's better at absorbing energy. And then we are now having more energy that's absorbed by the Earth system, probably keeping the atmosphere right above the Earth now warmer. So now we can melt even more ice. So now we can make the Earth even less reflective, lower the albedo even farther. So then we're going to have even hotter surface temperatures, melt more ice, and this starts to kind of snowball, pick up, and accelerate and accelerate. And so this albedo shift is one of the kind of climate drivers that we're observing now as we're melting out ice because of a warming atmosphere. We are absorbing a lot more energy on the Earth's surface and in the oceans relative to a time where we had more sea ice and more glacial ice cover. And so this is kind of accelerating a problem that we already had to start out with. And it's feeding on itself and becoming more and more exaggerated over time. So this is one diagram of sea ice change since the late 70s. And we're going to do a lab activity about this later on. Okay, so that's kind of the reflectivity component. Then the last component that we're going to mention is greenhouse gases. So I think most people are generally familiar with greenhouse gases. These are certain gases that enter our atmosphere, and they have a particular chemical structure such that they pass light, so light in the visible light spectrum, waves that are that right dimension to be visible light, and we call these short wave radiation. This light is sometimes called short wave radiation because the waves are a little bit shorter than heat waves. And these are really not impacted by greenhouse gases. The energy can rush right past a greenhouse gas, and the gas does not absorb that form of energy. However, when we have energy in the long wave radiation form, which is the infrared or heat wave form, the waves are a little bit longer. And when waves hit greenhouse gases that are in this dimension, the greenhouse gases absorb and trap that energy for a period of time. Okay, so if we have a lot more greenhouse gases in our atmosphere, we're going to have a lot more molecules that are trapping heat, both as it enters the Earth's atmosphere from the sun, but also that energy that comes in from the sun can be absorbed by the Earth's surface, and then it can be kind of re-emitted during the later in the day or later in the evening, and that heat that's leaving Earth is then trapped in the atmosphere, and it doesn't end up bouncing all the way back out to space. So the more greenhouse gases, the more energy we're trapping in the Earth's atmosphere. So even if we have a high albedo, if we have lots of greenhouse gases, then that energy that bounces off the Earth's surface isn't going to make it out to space. It's going to be trapped around the Earth and eventually warm the Earth up. So we have many different kinds of greenhouse gases in our atmosphere, things like CO2, things like methane, things like water vapor. So all those three examples are actually natural substances that have always occurred as part of our environment. We, in some cases, are increasing the concentration of these in the atmosphere in an unnatural way. But they are natural components. And then there's also certain kinds of fluorinated gases that contain fluorine, some of their chlorinated gases that we are kind of synthetic things that we have created that are pollutants in our atmosphere. But anyway, they are all contributing to greenhouse gas concentration in our atmosphere, and therefore they are holding this heat and they're warming our atmosphere up. Also things like ozone, nitrous oxide as well. And we'll talk about more of these when we talk about atmospheric pollution. Okay, so here's another graph. We looked at a graph before when we talked about how Milankovitch cycles seem to be somewhat correlated with the temperature of the Earth going back in time. This is another image showing the concentration of carbon dioxide, one of the dominant greenhouse gases, with temperature over time. And in this case, I would say that these two lines seem even better correlated than the two lines that show the change in temperature and then solar irradiance based on our understanding of Milankovitch cycles. So this purple line and this blue line are almost indistinguishable. They're right on top of each other, showing that these two variables track each other very, very closely. And so we have said at the beginning of the class that correlation like this doesn't always mean causation, but because we do understand a lot of the chemistry of how carbon dioxide and other greenhouse gases work, we do know that there is a direct cause here. As we have more carbon dioxide in the atmosphere, we said these greenhouse gases like carbon dioxide are physically able to trap the heat, which would cause the atmosphere around them to be warmer. And so we observe that in our own atmosphere. And so we can see that as the greenhouse gas concentration and carbon dioxide concentration in the atmosphere changes over time, we should absolutely expect that the temperature of the atmosphere will track very closely with those greenhouse gas changes. So this graph is going back 800,000 years in time, and it's showing we've certainly had times of lots of variability where we've had higher and lower CO2 gas concentrations, not higher than today, but variable. And those have tracked with higher and lower temperature. So if we continue to follow the pattern that we're on now, with continued increases in CO2 in our atmosphere, we should expect to follow this pattern of increases in temperature. So the last thing that I want to share as part of this lecture is thinking about how do we know about the greenhouse gases and the temperature of the past, right? That graph showed information going back 800,000 years. Anatomically modern humans have only been around for 200,000 years. And those humans did not have thermometers and were not writing down temperature and CO2 records of the atmosphere. So that data is something that's only very recently being recorded on kind of an annual or daily basis. Okay, so if we're looking to the past and trying to know about these atmospheric characteristics, we use what are called proxies. So we can't actually measure the temperature of a day 700,000 years ago, but we can make measurements. We can take empirical data of other things which we think are going to be closely correlated with the temperature of the past. So we can use those as proxies to help us understand what the temperature was like in the past. And one of the more common kind of climate and atmospheric proxies that we use is ice core data. So I have some images here showing how ice core data is collected. Basically, we have these huge hollow drills that drill down into these thick layers of ice in places like Antarctica or like Greenland, where they have lots and lots of ice that has been around for a long period of time. And they drill down into the ice and they pull out these columns of ice. And if you zoom into these columns, what you can see is that the columns have all these lines in them, and each of these lines represents a year. So just kind of in the way that trees grow one ring each year, areas of the earth that are cold enough to maintain ice throughout the summer form a layer of ice every year. And so we can look at these ice cores and we can count back and see how, first of all, how old they are. And then we can basically learn that we can learn some characteristics about what was going on in each year. So these ice cores can be very, very thick. They can have over 800,000 layers, representing 800,000 years that this ice has been forming. And when we zoom in even closer to these layers, we see that these layers contain tiny bubbles of air. And that air is basically a little tiny time capsule, a little capsule of the atmosphere as it existed in the year that that particular layer formed. So we can find little bubbles of air from last year, or from 50 years ago, or from 50,000 years ago, or 500,000 years ago. And we have a little sample of the air at that time. So first of all, we can stick a little needle into those bubbles, we can pull out the air, and we can learn just what was in the atmosphere. We can learn about how much carbon dioxide was in the atmosphere, how much methane, nitrogen, all these other gases, okay? And then we can also try to make an approximate estimation of what the temperature was at the time. And we can't do that by directly measuring the temperature, because the temperature would have changed, right? When we take that air and we put it in a place where we're measuring, that's changing the temperature of the air in the bubble. But instead, what we look at is isotopes inside the bubble. So we talked about isotopes at the beginning of the class. Isotopes are basically these atoms of the same kind, but that have different numbers of neutrons and therefore different weights. So for instance, in temperature proxies, we use oxygen isotopes. And so most oxygen has a weight of about 16 grams per mole, or about 16, but some oxygen has some extra neutrons. It's called oxygen 18. That's a heavier version of oxygen. And the idea is basically that heavier oxygen is harder because it's heavier. It takes more energy to keep that oxygen suspended in the atmosphere, okay? So if we take a sample of a gas bubble and it has lots of this heavy version, or relatively more of this heavy version of oxygen 18 in it, then it must have been a hot period of time in order to keep all that heavy oxygen suspended, because it would have required a lot of energy, okay? Whereas if we take a sample of an air and it only has the light version of oxygen in it, then it could have been colder and it was not having any heavy oxygen because it wasn't warm enough to keep those heavy oxygen atoms or molecules suspended in the atmosphere, they would have kind of fallen out. And so just basically like it takes more energy to lift up something that's heavier than something that's lighter. So if you're lifting up something that's heavy, you must have a lot of energy. If you're lifting up something that's light, that doesn't necessarily indicate that there was a lot of energy required. And so we use this as a proxy to estimate energy and temperature of the atmosphere by looking at these ratios of heavy and light oxygen. We also not only do this in ice cores, but there's other what are called Paleo Climate proxies. So paleo, ancient, climate, the climate, we know that. Proxy, a way to not directly measure, but make another measure that helps us estimate the climate of the past. And so another concept is that when it was hotter, when the climate was hotter, more ice was melting and entering the ocean. And so there would have been more of this light oxygen in the ocean water in times when there was more ice melting. And these oxygen atoms would then have been incorporated into different kinds of plankton, diatoms, and foraminifera, and corals. And so when we drill down and look at these ancient corals or these fossilized different kinds of plankton and shells and whatnot, we can look at the oxygen inside of them and we can make a determination of what the climate was like at that period of time when they formed. We can date these things using radiometric dating that we talked a little bit about at the beginning of the semester. And so anyway, these are the ways that we're estimating the atmospheric and climate conditions of the past. So that is going to be a stopping point. I'll give you guys a break and then I'll record another video for the next climate topic. Oh.